Hello there, I'm Jacob, and this is my lab view for motion of a falling object. So first of all, this is a simple lab comparison of three models that look at motion on a falling object due to gravity. One model takes into account air resistance, one ignores air resistance, and one of these models is based off of a real object. Just based off of this, I hypothesize that the three different models will be similar in shape, while the models with air resistance will slightly differ from those without air resistance. This whole lab is based off of Newton's second law of motion, which is momentum principle shown on the right, where F net equals delta P over delta T, and air resistance, which we'll talk about later. So what's happening, there's an experimental model that I took from dropping my rat cat from about a meter, and then used a tracking software to look at the values. And then a computational model that I used ClosesScript to create two computational models, one by just looking at the force of gravity pushing on an object for each delta T. So this is my video of me dropping the rat cap. And this is the application. You can see all the little points that I had to put on the rat cap as it fell to the floor. It traveled the distance that was close to 1 meter, 0.971, but I took account. So this is the video of my ball in the computational model. And this is all the code, but this is the important stuff. So we need initial conditions. You can take that from the tracker video and just import that directly in. We need the data printing, so we can copy that into our graph maker. And we need the hatch position, which can be controlled by setting forces, as you can see down in the bottom right corner of that picture, as well as using that function that will create a drag force, which we'll talk about now. So air resistance is a force that air applies on an object when it's falling through it. So the force due to air resistance is proportional to the velocity of the object squared for this lab. I solved for that constant here on the right. It's going to be about 0.5 for my object. And then you can apply this in ClosesScript to make a comparison to the real experiment. So let's look at the first two models. The Y position compared to the no drag computational model and the experimental model. You can see that the no drag computational model goes down a little bit faster because there is no air resistance on it. And then looking at that same thing, so for velocity, the experimental model is going to decrease at a slower rate in comparison to the computational model without drag. Same thing with just noticing the acceleration, the magnitude of the average acceleration is less than the magnitude of acceleration due to gravity, which would be negative 9.8. And you can see that trend line is at like negative 5.6. So then comparing all three of the models, you can see in yellow, the computational model with drag is going to be a lot closer to the actual experimental model itself, especially in position on the left. This is because both of these have air resistance, and it also proves that there is air resistance acting on the hat as it falls down. So what's actually happening? Our system and our surroundings. Our system is the hat in both models. And our surroundings is nothing in the initial computational model because I didn't code anything. But in the second computational model, as well as the experiment, it has a B value, which applies a air resistance, which would be the surroundings, I guess, is the air that acts on the hat. So talking about air resistance, solving for the B constant gives us a good standpoint, and it lets us estimate just exactly how much air resistance is acting on an object. In this case, it was very easy to look at the interactions because there were no other forces, and we could calculate it in correspondence just to record the values. And we could use this B value to find other information like the mass if we wanted to. So a lot of questions are like, what is a terminal velocity? Examine the terminal velocity, and this slide we're just going to talk about terminal velocity. So terminal velocity is when air resistance balances out force of gravity. This cancels out all the forces and it leads to a constant falling velocity. As you can see, that yellow curve is turning back up. You can see it especially towards the bottom, and that means that it would zero out and it would become constant. So then what does it mean that, like, if we added an initial velocity, would that change the terminal velocity? So initial velocities have no real effect on the velocity. That will lead to the air resistance force canceling out by gravitational. Because if you remember that formula, negative BV squared, like initial velocity is not in that. So using ClosesScript program, I proved this. There are three examples here. One where it starts from rest, one where it has initial velocity less than the magnitude, one where it has initial velocity more than the magnitude. All of those will return to that same value. It's like negative 4.4 in this situation. and thank you.